All right, welcome back to Unit 4. We're going to continue this unit with exponential or solving exponential equations. You may recall in our previous unit we were doing exponential functions, and we kind of did do some solving of exponential equations there, but we did it mostly by graphing or by using Desmos. In this unit, we're going to focus a little bit more on the algebra and hopefully not have to bring out any extra tools and just be able to use our minds to solve problems. Okay, we're going to start off with exponential laws in this lesson. I will admit that this is, for the most part, review. You should have done these all in grade 9 and 10. I'm going to shoot through the first part relatively quickly. If you're struggling with it, you can always slow it down or rewatch it. But for those who do have the prerequisites and are ready to go, I don't want to waste too much time on something that's pretty straightforward. So let's start off by doing kind of the exponent laws and build our way up to the more complex things. The first exponent law is what happens when we're multiplying two powers that have the same base. So a to the m times a to the n, for instance, and the rule is going to be keep the base the same, add the two exponents together. So for example, 7 cubed times 7 to the 5th should be 7 to the 3 plus 5 is 8. Now, just as a little aside, actually, if I want to show you how to do that by first principles, if you should ever forget how to do this, the first thing, 7 cubed, is 7 times 7 times 7. And then the second thing is 7 to the 5th, which is 7 times 7 times 7 times 7 times 7. And if I remove those brackets, because they're really not needed, really what it says is I'm multiplying 7 together by itself 8 times, which is 7 to the exponent 8. So for all these examples that I'm going to do, or the practice problems, just by all means, feel free to try them on your own and just double check afterwards. Skip the video, but I'm going to do them pretty quickly. Base stays the same at 2. Add the exponents. 3 plus 6 is 9, and not some weird oval that my computer just made. Negative 5 to the exponent 4 times negative 5 to the exponent 6. Base stays the same. Exponent becomes 10 because I add them. And not that you have to do this for this one, but you could write that as 5 to the exponent 10, since you know that an even exponent will get rid of the negative sign in the term. And here we have x to the 12 times x to the 21. Leave the base as x. The exponents 12 plus 21 is 33. All right, moving on to the next one. Very similar, except this time we're going to divide powers with the same base. So a to the m divided by a to the n is a to the m minus n. And just a quick note, this does not work for a equal to 0, because that would make the bottom of our fraction 0. All right, so over here, again, I'm going to do this one out the long way. 1, 2, 3, 4, 5, 6, 7 threes on the top, 2 threes on the bottom. And you know you can cancel out 3 on the top, 3 on the bottom, another 3 on the top, another 3 on the bottom. And what I'm left with, it looks like, is 1, 2, 3, 4, 5 threes multiplied together. Again, the quick way to do that would be 7 minus 2. But I want to show you that if you forget what the rules are, you can always go back to first principles and work them out from scratch. So again, pause if you'd like. Otherwise, I'll just shoot through these quickly. This becomes 2 to the 12 minus 3 is 9. This is negative 5 to the 8 divided by negative 5 to the 6, which is negative 5 to the 8 minus 6, which is 2. And you could write that as 5 squared. The question doesn't ask you to, oh, sorry, I lied. The question does ask you to evaluate if possible. In this case, we can evaluate. Did I skip that on the first one? Oh, bad teacher. Okay, and 2 to the exponent 9 is 512, a well-known fact everyone knows right off the top of their head. Or you could use your calculator or fingers. Sorry, I just want to go back up and check number 1. Did I forget to actually evaluate? I did. It says to evaluate if possible. Well, the good news is we just saw 2 to the 9 is 512. And 5 to the exponent 10. You know what? We could evaluate that if we want to do it on our calculators, but that's going to be a really, really big number. So I think I'm just going to leave it as it is. And x to the 33 cannot be evaluated since it's a variable. All right, final one. Leave the base the same, subtract exponents. 27 minus 15 is 12. Alrighty. Power of a power. If we have something in the form of a to the exponent m all to the exponent n, what we do is we multiply those two exponents. And just to show you this works, 6 squared is really 6 times 6, which really is 6 times 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 6. Again, I didn't need to know a law for that. That's just definition of what a power means. But when I look at that, I'm multiplying that 6 together 8 times. And again, could have found that much easier by just saying 2 times 4. So the first one is 3 to the power of 10. Again, that's going to be a fairly big number, but what the heck? Let's throw that in the calculator, see what it does. Yeah, we have 59,049. Second one, we're going to do negative 2 cubed to the 5th, which is negative 2 to the 15th. I know my answer is going to be negative because it's an odd number, and 2 to the exponent 15 is 32,768. And the last one is just variables, so there's no evaluating there, but multiply the two exponents together, and that becomes x to the 30th. And I'm kind of glad I didn't have to punch that in because anything to the exponent 30 is pretty large. Power of a product. So what this is saying is that we've got an exponent on a bracket that has something times something else in it. A, B is kind of the generic thing. The point, though, is that both A and B are put to the exponent m. And I'm going to just point out that this is usually used for things like this example of 2x to the 4th, where we have a coefficient and a variable. Both of them are going to get the power of 4. And again, to go back to first principles, that's 2x times 2x times 2x times 2x. And order of multiplication doesn't matter, so I'm going to do all the numbers first. 2 times 2 times 2 times 2, which is 16. And then x times x times x times x, which is x to the 4th. So again, could have done that faster by just saying 2 to the 4th times x to the 4th and evaluating the 16. This one here, I'm going to do it the ridiculously stupid way, but just to practice our rule and make sure it makes sense. This says it should be 2 cubed times 5 cubed, which would be 8 times 125, which would be 1,000. And of course, I think almost anyone with a brain would say, well, inside the brackets is 2 times 5. That's just 10 cubed equals 1,000. And you're absolutely right. That's how we would do it normally. But I wanted to show you that the rule works and that it does give the same answer as obvious math would. Okay, this one I'm going to do 5 to the exponent 4, x to the exponent 4. 5 to the exponent 4 is 625, x to the 4th. We can evaluate the 5 to the 4th. We can't do anything with the x to the 4th because it's a variable. And on this one, the negative 3 gets the square, and the x cubed also gets the square. Negative 3 squared is 9, and x cubed squared is power of a power, so that's going to be x to the 6. Power of a quotient works very similarly, except we do a to the m divided by b to the m. So for instance, x over 5 to the exponent 3 really means x over 5 times x over 5 times x over 5, which is x cubed over 5 cubed, or x cubed over 125. I'm going to keep pointing out that in math, you don't have to memorize a lot of rules if you can remember to go back to first principles and just do what it says to do manually. You can always kind of come up with the rule. It may take you an extra moment, but you'll at least be able to do it. So the first one for number 5 here is very similar to the one that we did at the beginning of number 4, where there's a really obvious way to do this one, but we're going to ignore that for a moment just to do our rule. And this says it's 20 cubed over 10 cubed. 20 cubed, 20 times 20 times 20 is 8,000. 10 times 10 times 10 is 1,000. So that just equals 8. Of course, the smart way to do that would be 20 divided by 10 is 2 cubed, which is 8. The next one, we do x to the 5th divided by 3 to the 5th. X to the 5th we can't do much with. 3 to the 5th would be 3, 9, 27, 81, 243, I believe. And by the way, at some point, someone's going to find one of these in the videos that I say something and write down something different, or just say and write something that's wrong. That's just mental math. I try not to do it too often, but it will come up. The last one here is going to be 2 to the 4 over x squared to the 4. 2 to the 4 is 2, 4, 8, 16. And the bottom, we multiply exponents for power of a power, and that's 8. This one's going to be our quickest one yet. A zero exponent just means that you have something equal to 1. And I do want to point out that that's only true if a is not equal to 0. 0 to the exponent 0 is undefined. It kind of has two competing rules. There's the rule that we're just seeing now that says anything to the exponent 0 is 1, but 0 to any exponent is 0. So this has to be 0 and 1. It turns out that neither of those is really accurate. It's a weird infinity problem. To show you why this is true, at the side here I put down 4 cubed divided by 4 cubed, which logic tells you the same thing on the top of a fraction on the bottom, so the fraction is equal to 1. But I could also over here, on the other version of 4 cubed over 4 cubed, I could say that that, according to our power rules so far, is 4 to the exponent 3 minus 3, which is 4 to the exponent 0. And what I just concluded is if this is equal to 4 to the exponent 3 over 4 to the exponent 3, and so is that, then they're equal to each other, which means 4 to the exponent 0 is 1. But the fact that I chose a 4 there is completely irrelevant. I could have chosen a 7 and then proven 7 to the exponent 0 is equal to 1. And so on and so on. Just one little aside for those. Actually, you know what? I'll save it for a little bit until I think we get to the next one. But I'll show you a cool little trick. This one I'm going to spend almost 0 time on. No pun intended with the 0 exponent. Negative 4 to the 0 is 1. 17 pi plus 1 to the 0 is 1. X minus 3 to the exponent 0 is 1. Assuming that x is not equal to 3. Because if x was equal to 3, then we'd have 0 to the exponent 0. So we're not allowed to do that, but for everything else, we just have 1 as the answer. This leads us to negative exponents. So it turns out that if you have a negative exponent, like a to the negative m, we can just write that as 1 over a to the positive m. Okay, so similar to the last one, what I'm going to do this first one is use the rule. Actually, sorry, for this one, what I'm going to do is write it out manually. I'm going to say this is 5 times 5 on the top, and then 1, 2, 3, 4, 5, 6 on the bottom. 2 of the 5s will cancel, and I'm left with 1 over 5 to the exponent 4. But I also know that the exact same fraction is equal to 5 to the 2 minus 6, which is 5 to the negative 4. And again, since the starting fractions were identical, that means that this must equal this, and the fact that it was 5 and 4 are irrelevant. Anything to a negative exponent is just 1 over the same base to the positive version of that exponent. All right, to do this super quick, 5 to the negative 4 is 1 over 5 to the 4, which is 1 over 625. 3/4 to the negative 2. Now this one's kind of neat. If you've got a fraction already, what you can do is just say that the top and bottom flip. So what we've done so far is take the reciprocal, the a goes to the bottom, but here we're going to move the 3 to the bottom and the 4 to the top, so we just flip that fraction and change the exponent to positive. And that's going to be 16/9. Same idea here. If we want to get rid of the negative exponent, we just flip this upside down to 4/x and make the exponent positive. That gives us 4 cubed, which is 64 divided by x cubed. Okay, and just as a quick little aside, you don't have to write this down. I'm just going to kind of show it to you for interest's sake. For those who have a hard time remembering the rule for the zero exponent and the negative exponent, I just want you to pick your favorite number. I'll choose 2 because it's easy to work with. And I'm going to write 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. I can stop wherever I want. I'll just do it this way. And I think you'll see that the answers to these are 2, 4, 8, and 16. So what happens each time really is every time my exponent goes up by 1, I multiply by 2, which makes complete sense. But likewise, that means every time I go down by 1, it divides by 2. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. Well, if I know that and I keep this trend going, I should divide by 2 every time I go down by 1. So 2 divided by 2 is 1. 1 divided by 2 is a half. A half divided by 2 is a quarter. And a quarter divided by 2 is 1/8. So we can see that just following that pattern upwards and downwards on that scale gives us what the zero exponent and negative exponents really mean. All right, now to do our examples there. Let's adjust the screen size again. Okay, so a to the 1 over, we did all our examples for that one. Now to move on to rational exponents. This one is something that may be new for some of you, and it's a little bit trickier. Most people don't think of it this way. But it turns out that a to the exponent 1 over n, or anything to an exponent that is 1 over something, is just actually the nth root of a. So if the n was a 2, it would be the square root. If n was the 3, it would be the cube root, and so on. To show you why that's true, over here I've got 25 to the 1 over 2 equals x. And 25 to the 1 over 2, well, what I could do is I could square that side and then square the other side. The equation's still balanced because I did the same thing to both sides. Now on the left, the rule for power of a power says multiply them together. Well, 1/2 times 2 is 1, so this just becomes 25. This becomes x squared. And then taking the square root of that, we would get x equals plus or minus 5. Now I'm going to be careful here. It turns out that the negative 5 doesn't actually work. It's just going to be the positive. I'm not going to get into the details of why that's true. For those of you who learned the plus and minus 5, the plus and minus 5 would be true if we started with this equation. But because we squared it in the first place, we lost that and then took the square root. And squaring and square rooting a number, we lose the negative sign. So only the positive is going to be the answer. But either way, if 25 to the 1/2 equals x and x is 5, it looks like it's just doing the square root of it. Similarly, if I take 8 to the 1/3, I could put that to an exponent of 3, as long as I put the other side to an exponent of 3. This becomes 8. This becomes x cubed. And then in order to solve for x, I would take the cube root of both sides, which means x is just 2. So I think you can see that anytime you're given a rational exponent, a fractional exponent, If it's 1 over something, it's just that root. Now the next rule, or the next part of this rule, looks a little bit harder, but if the fraction happens to be a fraction where it's not a 1 on top, we treat the top part like a regular exponent and the bottom part like a root. That one I've already pre-written down because it's like the complicated one. So for this one, what we're going to do is we're just going to say, let's take 81 and take the fourth root of that. So that's the bottom number, gives us the root. And the top number acts like a regular exponent. So the fourth root of 81, something times itself 4 times, that's going to give 81, would be 3 times 3 times 3 times 3, which is 9 times 9, or 81. So we know that in the bracket there we have a 3 cubed, and that is 27. So the bottom number gives us the root, the top number is a regular exponent, and we can actually do that in whatever order we like. However, if it's possible to do the root first, you're probably better to do this, because by the time you get to 81 cubed, that's equal to 531,441. Good luck at guessing the fourth root of that. But the fourth root of 81 is actually not too hard to do in your head without a calculator, because if it's a nice number, it's got to be 2 times 2 times 2 times 2, which is 16, or 3 times 3 times 3 times 3, which is 81, which works. And you'll get there very quickly. But try to find the fourth root of 531,441. Ooh, not something I want to do on my weekend. All right, let's try a couple of these. So we're going to skip a couple steps on these. We're not going to write the squaring of the sides and all that stuff. We're just going to acknowledge that 1 over 2 as an exponent is really the same thing as the square root. So something times itself is 49. That something is 7. Second one, 125 to the 1/3 is the third root of 125. So something times itself times itself. And again, I don't think it'll take you long to guess that that's going to be 5 times 5 times 5. By the way, these come into 2 categories. They work out nicely or they work out horribly. The nice ones you can do easily without a calculator by kind of guess and check. And the tougher ones you've got to use a calculator for. And you can use your calculator by putting in a fractional exponent or by putting in the actual root as it's written. Okay, 32 to the 1/5 is the fifth root of 32. That would be 2 times 2 times 2 times 2 times 2, so 2. For this one, we treat the 2 on the bottom as the root. I didn't have to write the 2 there because without it there, it's still a square root. But it's the square root to the exponent 3, which is 5 cubed, which is 125. This one is the fifth root of 243, all cubed. And again, you can guess what it is by just trying a few easy ones. 2 to any exponent is going to be even. 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. So yeah, it looks like it's going to be 3 cubed. And 3 cubed is 27. And finally, this one's going to be the seventh root of 128, all cubed. And we're looking for a number multiplied by itself 7 times. I would definitely start off at 2 here because anything times itself 7 times is going to get very large very fast. And sure enough, if you do 2 times 2 times 2 times 2 times 2 times 2 times 2, you'll get 128. So that becomes 2 cubed, or 8. Okay, and if you could do these, all these ones here, I haven't touched a calculator for. If you'd like to practice using your calculator to put in those exponents, you're more than welcome to. I will, however, ask you on the test, I believe for this question, I will specifically say to convert it to radical form, which is a fancy way of saying I want to see something with the square root signs, and then work from there. So if you just punch in, for instance, 128 to the exponent 3/7 and you get 8 in your calculator, I won't give you any marks. You got to show me this method of doing it where you're using the radicals. You're basically changing between fractional exponents and roots. All right, the last part here is really nothing new. It's just actually combining the laws. And I know that most students can get the individual laws right, no problem. But as soon as they're confronted with a bunch of them in one question, all of a sudden every piece of knowledge is lost. So let's go through here and see what happens. This first one here, let's work, I guess, with this bracket first. Remember, we start off our expressions with equal signs. So 3x cubed means 3 cubed times x cubed times 2x cubed over x to the negative 2. Now, by the way, at this point, you can actually bring that x to the top and make it a positive 2 as an exponent, because that's all a negative exponent does, is basically moves tops to bottoms, bottoms to tops. However, we can use a different rule in just a moment. Either way is acceptable, but I'll just use this other method for 1 second. Now on the top, we have 27 times 2 is 54. X cubed times x cubed is x to the 6th, because we're adding the exponents. And then the last rule, 54, stays the same. We have x to the power of 6 divided by x to the negative 2, so we subtract exponents, and 6 minus negative 2 is 6 plus 2 is x to the exponent 8. Which you could also see if you moved the x to the top, you'd have x to the 6 times x squared on the top, which is also x to the 8. So you get the same answer either way. For part B, we can deal with this negative exponent right off the bat, but let's actually do the brackets first. Let's try and follow the BEDMAS rules. Okay, so inside the brackets on the top, 3x to the 0, a whole bunch of people are going to write down 1 for this, but the answer is actually 3. 3 does not get the exponent of 0, just x does. Now, as soon as I say x to the exponent 0 is 1, I'm going to make a little note over the side here that x cannot equal 0, because if it did, we'd have 0 to the exponent 0. Okay, so that's our first bracket. And then our second bracket is just an x cubed. And our third bracket is 3 to the x. And on the bottom, I could do a little simplification there. Power of a power, multiply the exponents, and get x to the 4. And then that whole thing is to the exponent negative 2. Now I can simplify that a little bit. On the top, I have 3 times 3 is 9. X cubed times x is x to the 4th, divided by x to the 4th, all to the negative 2. And I can use either my power divided by a power rule and say it's x to the 4 divided by x to the 4 is x to the 0, which is 1. Or I can just look at it and say the x to the 4 and x to the 4 cancel out on the top and bottom. And then I'm left with 9 to the negative 2, which becomes 1 over 9 squared, or 1 over 81. So it's equal to 1 over 81 in all cases except x equal to 0. Just for the heck of it, I'm going to bring up Desmos for just a second, and I want you to see what this looks like. Okay, so I've just typed that into Desmos there, and you'll notice it's a straight line. I'll explain that in a second. Well, I won't actually explain it in a second. I'll explain it right now. We got that this function, we had an expression. I'm just setting that expression equal to f at x so that we can actually get a graph of it and see what it would look like as a graph. But we said that the answer to it was 1 over 81. So basically x is getting close to 0, which is why it's so close to the x-axis. But if I zoom in enough, you'll see it's not actually on the x-axis. It has a height of 0.012345 I bet you it's 6, 7. But anyway, which happens to be 1 over 81. Okay, so the y value is always going to be that, but we said that it wasn't defined at x equals 0. So let's see what Desmos says as I get closer to 0. It says the y value keeps staying the same, keeps staying the same, keeps staying the same. But right at 0, it says it's undefined. So this actually isn't a straight line. It's a straight line with a little hole in it. One little missing single number. right at x equals 0. So Desmos is smart enough to know that x equals 0 makes this basically evaluate to nothing. It does not exist. Anyway, I thought I'd just point out that Desmos does recognize that, which is kind of cool. All right, going back to our questions. We'll do just a couple more of these and then I'll let you go. Okay, so for the first one, where'd my sheet? There we go. My sheet disappeared for a second. Again, I can deal with the negative exponents by flipping things from top to bottom or bottom to top, but just for now, I'm going to kind of leave them as they are. We'll deal with them later. So on the top, I have 3 times 2 is 6. X to the negative 1 times x is going to be x to the 0, which is 1. So I'm not going to write it, but again, x to the 0 equals. So x cannot equal 0, because if it does, it breaks it. It actually breaks it in several places. All right, so the top is 6. And on the bottom, we have 2 times x to the 0, which is just 2. And again, x can't be 0, but we already dealt with that as a restriction. And on the top, we get 6. And on the bottom, we get 1 over 2 cubed, or 1 over 8. Now, we could have just moved that 2 to the negative 3 to the top to get 8 on the top. Really what we're doing is we're doing the 1 over 8 and we're multiplying top and bottom of the fraction by 8 to keep it equivalent, which gives us 48 on the top and 1 on the bottom. So you can think of it as moving 2 to the positive 3 to the top, or you can do 1 over 8 on the bottom, evaluate 2 to the negative 3 as 1 over 2 cubed, and multiply top and bottom by 8, whichever makes you happier. All right, finally, for part D, this one's looking kind of nasty. But again, we just tackle it one piece at a time. The top we can't do much with. On the bottom, we have 3x squared all squared. The 3 gets squared. The x squared gets squared. And then we have 9x to the 6, all to the negative 3/4. All right, now we have still x squared on the top, but on the bottom we have 9 times 9 is 81. And we have x to the 4 times x to the 6 is x to the 10th, all to the exponent negative 3/4. I'm going to cancel out 2 x's on the top and 2 x's on the bottom, which gives me 1 on the top and 81x to the 8 on the bottom. And finally, I'm going to get rid of that negative exponent by flipping the fraction inside. So inside the bracket becomes 81x to the 8 on the top and then 1 on the bottom, but we don't bother writing that. So that changes our negative 3/4 to positive 3/4. Then what we have to do is deal with that 1/4 part. So remember, we've got a 4 on the bottom. We're going to take the 4th root. So we'll take the 4th root of 81x to the 8. But we still have the 3 up there from the top of the fraction. Now the 4th root of 81 is just 3. And the 4th root of x to the 8 is x squared. X squared times x squared times x squared times x squared is x to the 8th. That still gets cubed. And then finally, 3 cubed is 27. X squared cubed is x to the 6th. And that's our final answer. So simplifying those makes a significant difference. We should put a little restriction on here. Again, going back to the very original equation, we have an x there, an x there. If either of those is 0, the bottom of this fraction is 0. So this is what it's equal to. But again, provided that x is not equal to 6. Not equal to 0. Looking at the wrong number. And again, I'm going to go back over to Desmos to show you what that looks like on our graph. A little bit different than the last one. Okay, so I've gone into Desmos and I've put in that expression as a function. Again, technically it's not a function because it was just an expression with no equal sign in it, but if we wanted to graph it, this is what it would look like. For the different x values, these are the y values that come out. And we get something that looks like a parabola basically with a flatter bottom. So we know that our parabola here, or sorry, it's not a parabola, that our polynomial function simplifies down to 27x to the sixth. So that was our answer. And if I just put our simplified version on this, you'll see it's exactly the same shape, or at least almost exactly the same shape. It looks almost identical when I keep turning it on and off. And if I zoom in or zoom out, I think you'll see the same thing. It still looks the same shape. They cover each other up nicely. But the one difference is that we said that it's only equal to 27x to the sixth if x is not equal to 0. And if I zoom in enough here on this one, if I turn on the blue one, you'll see that at 0, sure enough, when I plug 0 in, I get 0 out to 27x to the sixth. However, if I plug 0 into the red function, I get undefined. So that's why we had to put that little extra restriction on there, just saying that at a brief point at x equals 0, that whole thing becomes undefined because we have a 0 on the top, a 0 on the bottom. 0 on bottoms of fractions are always going to be troublesome. So we're going to run into that issue. But other than that, it looks like 27x to the sixth. Okay, I'm going to stop there. The only thing left in this lesson to do is a couple of practice problems. Try them, see if you're getting them right. If you're not, seek help. And if you're getting them right, that's fantastic. But yeah, any trouble you've got, let me know. I'd be glad to help. And otherwise, I will see you in the next lesson.